Last time we talked, I got into a little bit of telling you a little bit of the history of Kepler and Brady and Aristotle and all that sort of stuff. You'd be surprised to figure out or to find out all the stuff that even the ancient Greeks and to some extent the ancient Egyptians knew. So the ancient Egyptians really were the first culture, as best we can tell. Lately we've been teaching at the university and college level, we've been teaching world history as opposed to just European history. But it still seems like basically the cradle of life was Northern Africa / Egypt. That's where the first civilizations developed. However, there were civilizations, there were pre-civilizations going on in North America, South America, Africa, and also Europe and Asia, stuff of that sort. So we're learning more about that, but we are still somewhat European centric. But what we do know is that the ancient Egyptians had, in fact, made sense to some extent of the sky and how that worked. And that's absolutely essential for you to be a colony. Excuse me. For you to be a civilization that, can, for instance, reward art or create literature or create music, stuff like that. You cannot be the type of culture that spends 100% of your time hunting and gathering. So you really need farming, and you can't farm, at least on a planet like Earth, you can't farm without an understanding of the seasons, and you can't understand the seasons without an understanding of the sky. So we know, for instance, that the ancient Egyptians understood a lot. Well, I shouldn't understand, it's sort of the wrong word. They had realized a lot of patterns that allowed them to realize things like, okay, well, we're going to have the Nile flooding around such and such a period. That is commensurate with us doing this in the crops and stuff like that. And just little things like that. In fact, what you notice is there was a star that they discovered that had what's called a heliacal rising. And that means the star will rise in the east one morning, and then almost immediately thereafter, the sun will rise. That day is the heliacal rising for that star. And what they discovered is that particular star did that on the day that the Nile flooded. With some crops, a flooding would mean you've wasted them. With other crops, a flooding would mean now it's time to pick them. And other crops, it means, well, we got to do something quick. So that was kind of a big deal. But what they really needed was a little bit of a warning. So they watched and watched and watched. And ultimately, I apologize. I don't know why I keep yawning. Ultimately, what they discovered was there was yet another star that rose, had a heliacal rising 2 weeks earlier. And that first star that we talked about turned out to be the star they call Canis Major. And it was, it really is the brightest star in the night sky. And it's so bright, in fact, that the ancient Egyptians and many other cultures believe that one of the reasons the summer was warmer during the summer was specifically because not only was the sun up during that part of the year, but that star Sirius in Canis Major, I called the star Canis Major a second ago, sorry about that, but that star Sirius, the dog star, was actually up during the day. So they literally thought that that contributed to the weather, and therefore that's why we had summers that were so much hotter than, say, winters. And that star that they discovered actually had a heliacal rising 2 weeks earlier, was a star that they named Procyon or Procyon, which means before the dog. So Sirius was called the dog star. It's where we get phrases like the dog days of summer. It's also where Sirius satellite radio got their dog mascot, because Sirius is the dog star. It's in the constellation of Canis Major. That makes it the big dog. Procyon, on the other hand, is in the constellation Canis Minor, which, to be honest with you, really has two bright stars, and that's it. But the fact that it rose 2 weeks earlier is super helpful. So they didn't care too much about knowing exactly why the stars rose and the stars set and stuff like that. But they did know that the stars' position mattered and that things repeated over time. And that, in fact, you could use that as like a giant clock slash calendar. So not only is the night sky a clock from night to night to night, it's also a calendar from week to week to week to week to week. And that's sort of what you need on a planet like Earth to have a culture in which you can farm. And of course, a culture that can farm means that you've got a certain fraction of the population that's farming, getting food, and then other fractions of the population are doing other things to trade for food. Dang it, that was terrible. So that's what came on with Egypt. And in fact, we've got records, historical records from Egypt that go back to, 2, 3, 4,000 before the Common Era. So that used to be called BC, and then AD is now called Common Era, which means it's partly different because originally it was before Christ and Anno Domini. But basically, we now know that Christ wasn't necessarily born on the same time, on the same date that we thought he was. Not only that, Christos has some meaning of ordainment or something like that, and not every religion, of course, recognizes Christ as that Christos. So it's a little more politically correct to refer to it as the Common Era and before the Common Era. So we use that. But the main thing is you can go several thousand years before that time, BCE, and we actually have records of stars at that time. That's actually large enough amount of time for us to see major changes. For instance, we know in ancient Greece, they had ancient Greece. In ancient Egypt, they had a period where the North Star was not what we call the North Star now. Our North Star, which is a star is very close to directly over the North Pole of the Earth, is a star by the name of Polaris, which is the end of the handle of the Little Dipper, or Ursa Minor. And in fact, you can use the front two Dipper stars of Ursa Major, Merak and Dubhe is what they're called. You can form a pointer from those stars going from the bottom of the Big Dipper pan to the top front edge of the Big Dipper pan, follow that line straight up, and that will point you right to Polaris, the North Star. That star, like I said, is very close to directly overhead at the North Pole. And because of that, it appears like you're looking at a record player or a CD player or a DVD player, and there's one part dead center on those things that doesn't move. That's what the North Star looks like. In fact, the North Star is making this itty bitty circle, but we can't tell it too well unless we actually do some measurements. So that's our North Star, and it turns out that at least part of the time of ancient Egypt, they had an entirely different North Star called Thuban, and Thuban's in the constellation Draco, and Draco sort of winds between the Dipper of the Big Dipper and the Dipper of the Little Dipper, and then it goes around the Big Dipper and then curls back around, and its head is down like about to bite the constellation of Hercules, and that star Thuban used to be their North Star, and we can see that in some of the hieroglyphs and stuff that they left in etchings. You can see that they put a lot of attention on that one star and a lot of attention on what we now call Ursa Major and Ursa Minor. Not only that, we know, for instance, that we have the Tropic of Cancer and the Tropic of Capricorn, and the Tropic of Cancer basically was named that because the sun was in the constellation of Cancer on roughly 6/21, which is the summer solstice. And on that day, because of its location in the night sky relative to the Earth, or excuse me, in the day sky relative to the Earth, the sun casts no shadow at 23.5 degrees north latitude, which is, of course, the Tropic of Cancer. And then that's around 6/21, can be 6/20, can be 6/22, something like that. And then around 12/21 is the winter solstice. And at that point, the sun is directly overhead of 23.5 degrees south latitude. And that latitude corresponds to Capricorn, the Tropic of Capricorn. And on that day, the sun was in the constellation Capricorn. But because this, was started in the time of ancient Egypt, the Earth has precessed enough since then that that's no longer the case. So, for instance, if you look on, 621 roughly, you will find that the sun is not in Cancer anymore. And if you look on 1221, you'll find that the sun is not in Capricorn anymore. And if you look on the dates that my horoscopes say make me a Gemini, you will find that I am no longer a Gemini. I'm actually, I think, a Taurus, if I remember correctly, because what made us what we are as far as astrological symbols is exactly where was the sun when we were born. So you can take up any astronomy software, for instance, heavens-above.com is one such a place. You can put in your particular address. It'll tell you exactly what you're going to see at your particular time of day and all that. And then you can dial it back to the day and even the hour and minute you were born and look what constellation the sun was in. And that's your quote unquote true astrological sign. Astrology is a pseudoscience we've now learned because we've learned the techniques of science and things like double blindness and things like confirmation bias, stuff like that. And we realize that it really doesn't hold any bearing, but still, if you're interested in astrology, we're just tickled to have you in our science class. Okay. So because of all that, we now know a lot of different things have happened with our solar system. And remember, when we're talking this time, and even up through the time of Copernicus and Galileo and Newton, when we say the universe, we mean basically our solar system, which is the sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. And they didn't even know about Uranus, Neptune, and Pluto at that time. The asteroid belt, they didn't know about that. The Kuiper belt, they didn't know about that. The Oort cloud, they didn't know about that. They knew about some of the gas and dust probably. And they knew about a couple thousand stars, maybe as many as 6,000 or 7,000 stars, but that was the entire universe to them. They didn't understand that there were other islands of stars like our Milky Way, and that Andromeda was one of them. In fact, that didn't happen until Edwin Hubble made the observation of Andromeda with a 100-inch telescope. And that was in the early 1900s. So prior to the early 1900s, the universe was just that little part that I told you. Now, we had a model of the universe and it worked, and it was relevant in that governments try to make decisions that were astrologically sound. So, for instance, there was this whole mythology of astrology that would say, well, if the sun happens to be in the constellation of, let's say, or excuse me, if Mars happens to be in your birth constellation, maybe that's not a good time for you as the king to go to war. Okay, because Mars is the god of war. Maybe it is a good time. I don't know. And in fact, you can get two different astrologers that'll tell you two different interpretations on that, or maybe even four different interpretations. But that was a relevant thing. Not only that, you had certain holidays and religious holidays, especially, that were very much related to astronomical events. For instance, even Easter, you'll notice that Easter is always on Sunday, but it's not necessarily the same Sunday every year. They have a very strict set of rules. I should have looked it up before I came in, but basically it's something along the lines of it's the first Sunday after the first full moon after the vernal equinox, something along those lines. And the Friday before that, of course, would be the Passover Friday. So you've got these astronomical events that can predict dates, for instance, Easter. And therefore, governments and civilizations need people that can calculate where these things will be. Where will be the planet Mars on such and such a date? Where will the planet Venus be, and so on and so forth? And you know, those things were named gods and named after gods. And for instance, the one planet that went from, say, the constellation Sagittarius to Sagittarius again in the shortest period of time seemed to be very fast, so they named after the swift messenger god called Mercury. Of course, that was a different god when it was the ancient Greeks. So we're left with the ancient Romans version, because they were the last great civilization that gave us those names. So we don't use the Greek names, we use the Roman names. And it turns out, in fact, the objects that we can see in the sky are why we have 7 days in a week. You can trace the etymology of the names of the individual weeks, and certain ones are obvious, like Monday sure does look a lot like Moon Day, and Sunday sure does look a lot like Sun Day, and Saturday looks a lot like Saturn Day. But some of them are a little more obscure, like Wednesday and Thursday. You can sort of get Thursday from Thor, but it turns out if you trace the words back, they each point to an object in the sky. So that's why we have 7 days a week. Now, in addition to all that, we had this model set up. It was set up by Eudoxus. It was set up by the Pythagoreans. And every 10, 20, 30 years, it would be updated, because they'd have another 10, 20, 30 years worth of data, and they would try to fit it. And it was a bit problematic in that every time they look at the data, it would look a little different than last time. And what they'd want to do is make an almanac, like a collection of pages that someone can just go to and say, okay, in this year, exactly where is Mars going to be? Exactly where is Venus going to be? So that's what astronomers, who didn't really differ from astrologers in many cases, that's what they did. They would take the models that were made up by people like Ptolemy and Eudoxus and the Pythagoreans and all those guys, and apply them to figure out what months and what days, which stars would be where, what constellations would be where, what planets more specifically would be in what constellations. Okay, that was their job. We had a geocentric model of the solar system and therefore the universe for a long period of time, but it wasn't out of stupidity. For instance, the ancient Greeks, one of which was Anaxagoras, had considered the idea of a heliocentric universe, but they realized that if such a thing existed, if in fact the sun was, say, right here, and the Earth were to, say, orbit around it, then what you might see is when the Earth is over here on this side of the sun, they might see this nearby star looking like it's right in front of, let's say, the star that I've got marked on my desk right there. That's really just a grain of wood. But when the Earth is over here on this side of the orbit, it can still see that same star, but now that same star is in front of the handle on the cabinet of my desk. Okay, if that handle and that grain of wood were actually more distant stars, what we would see is that this star that's sort of closer to us seemed to have wiggled from the grain of wood to the handle, the grain of wood to the handle. That's called parallax. And they looked for that. They did not see that. They could not see any moving of any stars. And from that, they reached two possible conclusions. One conclusion was that, wow, the universe is ginormous, and they just could not imagine the universe being that big that they couldn't measure that. The other one was, we're not moving. Okay. So rather than choose the universe being so big that they couldn't believe it, they chose the latter, which was that the universe wasn't that big. It just happened that we were the center of it. So the Earth is at the center of this galaxy, or excuse me, of this universe, and that's the way things are. But we had other descriptions that had to be taken into account. So let me show you how those were taken into account, and then I will also give you a little bit more details on what we're going to use from Kepler's laws and that sort of thing. So here I'm going to share screen real quick, maybe. Okay, looks like it's working, so that's a good thing. So one of the things that was noticed early on, in fact, we do this in our astronomy, we can take like a little computer program and we can just run back and forth in time with this computer program and see what's the farthest angle that, say, Mercury makes away from the sun at any time of year, and what's the farther angle on the other side. And what we find is Mercury and Venus both have a limit to how far away from each other they go. So we had to make sense of that. Not only that, we had to make sense of the fact that there were, in fact, stars that we would see. And I've sort of done this before, but I'll draw this one again. So there's a constellation out there that looks sort of like this. Okay. Anybody recognize that constellation? I think the lower right hand side almost looks like a mirror image of the upper left hand side, and that's on purpose because this is the constellation Gemini, the twins. So in general, the neat thing about the stars is they look this way tonight. It happens to be that that Gemini is actually up during this time of year. It's a winter constellation. And you can go out and find it. And in fact, you can go out 2 hours later and find it again, and it's always going to be shaped like that. And if you wait too long, say 2 or 3 months, then you won't be able to see it at all. But if you come back again in February of next year, you will see it again. And not only that, it'll look exactly the same. So those things were very convincing to the ancients. So they imagined, in fact, that the Earth was the center of the universe. And according to Aristotle, the heavens were perfection, and perfection means that only the most perfect things can be out there. They're immutable, meaning they're unchangeable. So the rules were that if you're in outer space, which is the heavens, then the perfect shape is the sphere. So everything has to be a sphere, or maybe just maybe a circle, but those are the perfect shapes. Ergo, that must be what's in space, i.e. heavens. Not only that, you can't have things change. You can't have objects speed up or slow down, because if they sped up, they were speeding up to the perfect speed, and therefore were at a non-perfect speed before, or vice versa. So that was sort of some of the logic that was used with Aristotelian science. And that had to be dealt with as well. So what they imagined was there was a giant crystalline sphere centered on the Earth. And outside of that sphere, one of the common ideas was there was fire. And in fact, that sphere had very specific holes in it. And in fact, you can see 1, 2, 3, 4, 5, 6, 7, 8 of those holes right there in the blue dots that I drew. So those blue dots were shaped like that because they were actually holes in a giant crystalline sphere through which fire would blink through those little holes, and we would see the fire, and that's why the stars would twinkle. Okay, so that was sort of their idea, and that explained everything. And the giant crystalline sphere would rotate around us, and that is completely consistent with the way the stars appear to move. In fact, it's so consistent that we still use that crystalline sphere model as a first order approximation when we teach students how the stars move from hour to hour, day to day, and stuff like that. So it really is pretty accurate. Now, the weird thing was the ancient Greeks discovered that every now and then they would get a weirdo into the realm of, say, this particular group of stars. And that weirdo, if you waited a few days, might end up over here. And then a few days more end up over here, and then here. And then as the time got further and further, it might even get brighter and brighter That's why I'm showing with the big ones. And then they get less bright, less bright, less bright, and then go back to about the same brightness it had and wander off. And they would say it's as if it wandered through the other stars. And the ancient Greek word for wanderer was planetos. So that was the ancient Greek word for wanderer. And it made perfect sense because these wanderers were doing something that couldn't be explained by talking about crystalline spheres. So they had to make up for that. They had to make up for that weirdness of them doing loop-de-loos, but they couldn't change the heavens because the heavens were perfection. And therefore they had to stay in spheres and stuff like that. So in an attempt to explain, one, Mercury not getting very far from the sun, two, Mercury showing loops like that and getting brighter at some times and less bright at other times, three, Venus doing the same two things, and three or four, all the other planets doing loops like that as well. In order to explain all that, this was the model they came up with. So here's a little itty bitty Earth right here. And then centered on the Earth was a deferent, which is sort of like an orbit around the sun, around the Earth, excuse me. And in an attempt to make sense of what Mercury was doing, they would have an epicycle on it. And an epicycle is like a circle on a circle. So if you ever watched Bug's Life when they said tunnel within a tunnel, that was sort of a paying homage to this crazy time. Now, here's the trick. In order to make sure that everybody understood that this was Mercury and that Mercury behaved like it's supposed to, they had to imagine a line that connected the center of the Earth to the center of the sun. So there's our sun. And that line had to have the center of Mercury's epicycle on it. So what they pictured was Mercury, say, going around this epicycle that way, while, of course, the sun would travel that way, the Earth would rotate this way, and therefore the epicycle would travel this way along the deferent. And the fact that Mercury gets brighter just comes from Mercury being, say, on this side of the circle. Venus had to do the same thing, but Venus got further away, so Venus's epicycle was bigger. And again, its epicycle, of course, would have also been on the center, and its deferent would have been like this. And they had a lot of degrees of freedom to tweak this. So they could tweak the rate at which Mercury would go around its epicycle. They could tweak the rate at which Venus would go around its epicycle. They could tweak the radius of the epicycle. They could tweak the radius of Mercury's epicycle. Not only that, they ultimately even moved the Earth away from the center and made an equipoint and all this weird stuff. Then outside of the sun's orbit, which the sun, of course, orbited, it didn't make any loops, so it just had a regular orbit. But outside of that, you had, of course, Mars, and Mars would actually have to have an epicycle as well to explain its loops. And then outside of that, notice they didn't stick to the line like the other ones did. Then outside of that, actually, we had Jupiter, which would have a different epicycle. And then Saturn, of course, with a different epicycle as well. So you can tweak all those things and you get them mathematically to fit all the data that you'd seen in the last 10 or 20 years. And then you predict what the next 10 or 20 years would be, and you'd publish your almanac and the government would pay you. and that worked all fine and all that good stuff. But in the intervening period, a guy by the name of Copernicus comes along and says, wait a second. And this is why I have a distinct difference between the Copernican revolution and the scientific revolution. Copernicus did not say, oh, this data just does not match reality, so we can't use this anymore. No, Copernicus said, I think with all these epicycles and difference and equipoints and all this junk, we've lost our way from what Aristotle taught us. We should go back and figure out what we can do. So what Copernicus does is Copernicus goes and makes a heliocentric model. In other words, one with the sun at the center. And then things like Mercury being always close to the sun and Mercury being the fastest around is just a natural ramification of its orbit being the smallest orbit and therefore it being closest to the sun. Then Venus and its orbit's second closest, then the Earth, then Mars, then Jupiter, then Saturn. And he could even explain the retrograde loops, as they call it. For instance, when the planet was going this way, it's actually in retrograde. It's going the opposite direction it normally goes, and it was actually brighter. That could be explained with Copernicus's idea as well as just basically the inner planet catching up with the outer planet and then passing it. So sort of like you going, let's say 58 in a 55 mile an hour zone, but you're in the left-hand lane. This car going 60 passes you. If you're sitting sideways in your seat, you see them coming from right to left as they pass you. Then all of a sudden you get to the spot in the road where you're on the inside track. And all of a sudden you see that car that was going from your right, which is the rear of your car, to your left, which is towards the front of your car. That car slowly comes to a stop with respect to you and then starts backing up, not literally, but relative to you. In other words, you start passing it. So it starts going from your left to your right. You end up going past it. And then the road becomes straight again. And the fact that you're going 58 and they're going, say, 62 makes the car go from right to left again. So this retrograde that I showed you here is just what's going on with the outer planets. They're going slower, but in general, you only get to see that when you're passing by them nearby on the inside lane. So Copernicus could explain all that, but Copernicus had stuck to Aristotle's rules, and he stuck to only circular orbits. He stuck to only circular orbits in which the planets went at constant speeds. And in fact, all that just didn't work. Kepler gets gets a job with Brady and starts using their data. Brady has his own model, and let me just briefly give you that. So Brady's model is basically a little bit like Copernicus. You've got the well, let's do it this way. You've got basically the sun. Oh, we've got the Earth, the sun right here, say, and then we've got the Earth over here. I'll label this the sun. I'll label this the Earth. And what we're going to have is, in fact, everything orbiting the Earth, or excuse me, the sun. So there's Mercury, there's Venus, so on and so forth, Mars. All of those are orbiting, but here's the weird part. The sun is actually going to orbit the Earth. So that's what Brady's model was, which was just crazy. Kepler's model had a different spin. Kepler's idea was it couldn't be coincidental that the number of heavenly bodies was exactly the number you'd need if there was one perfect solid between the sun and the planet Mercury, and then there was another perfect solid between the planet Mercury and the planet Venus, and then another between Venus and Earth, another between Earth and Mars, another between Mars and Jupiter, and then finally another one between Jupiter and Saturn. So he tried to work it out that way. Well, when he finally gets the data, because poor Brady dies. Tycho Brahe's party so hard one day, and being a proud nobleman doesn't want people to know that he poos and pees. He refuses to leave the table, even though he's drank a huge amount of drink and ate a huge amount of food. His bladder bursts and he becomes septic and dies a horribly painful death, all out of pride, basically. Kepler has to fight to get the data, ultimately wins in court, and Brahe's family's fighting it because they're afraid he's going to steal his thunder. And of course he does. I mean, look at how many people have heard of Kepler and how few have heard of Brahe. But to Kepler's credit, Kepler takes the data. He first tries his own model. That fails. And no matter the fact that it took him years and years to work out all the math of his model, when he found it didn't work, he just threw it away. That's just, that's what you got to do as a scientist. I don't care how much you love it, you throw it away. He took Brahe's model, that didn't work. He took Copernicus's model, that didn't work. And in fact, it all hinged on one small little parameter about Mars's orbit. And that one small little parameter was so small that it could have been just swept under the rug as instrumental error. But his great respect for Brahe, even though they, like I told you, Brahe would sort of be like the Russell Brand or the Jonah Hill or the Seth Rogen, if you will, of modern day times. And Kepler, not from a political standpoint, but from a upright, pious standpoint, would be more like a Mike Pence character, who literally will not, be in a room alone with any woman other than his wife. That's the kind of person that Kepler is. And you can imagine those would bump heads a little bit. But still, when push came to shove, Kepler, one, dedicated his book to Brahe, and two, he trusted Brahe's data so well that he was even able to throw away the Copernican model, throw away his personal model, throw away Brahe's model, all in search for a model that fit Brahe's data best. Okay, so that's what he did. What he ultimately had to conclude was this. The planets, he said, orbit in elliptical orbits with the sun at one focal point. So they're elliptical orbits, which is kind of an oddity, but let me show you what that means. Basically, what that means is that you could make, on a sheet of plywood, you could, for instance, make a circle by putting a nail in it, tying a rope to the nail, and then pulling the rope taut and making sure you hold it taut, and then holding a pencil and making sure you keep that pencil vertical the whole time, and make sure you don't stretch the rope. That would trace out a perfect circle. So that's the circle. That's fine. We all get that. And that was the orbit that Aristotle would have expected. That's the orbit that Copernicus would have expected. But what Kepler said is, no, they're elliptical orbits. And the way you could make an elliptical orbit is you could imagine, for instance, putting a nail here and another nail here. So instead of one nail, you're going to have two nails. And instead of a string tied to a pencil or pen, you're going to tie one end of the string to one nail and the other end of the string to another nail. And then you're going to stick a pencil in there to keep it nice and taut. Now you're going to, without stretching the rope and without letting the rope or string get loose, you're going to pull that around and around and around and around. And well, that was pretty good, but not quite. And what you ultimately get is an ellipse. And that's what Kepler said these shapes were. Now, this is particularly remarkable for Kepler because it turns out Pluto was like the worst case scenario. And if you actually took a exact replica of Pluto's orbit again, he didn't actually look at Pluto's orbit, but Pluto's the worst. So that's why I'm using it as a gauge or whatever. If you actually take a look at Pluto's orbit next to a similarly sized circular orbit, you'd have to do quite a bit of measurement with rulers and stuff like that before you could realize that, in fact, Pluto's orbit is the non-circle, it's an ellipse, and the other one's an actual circle. So that really speaks volumes about how good Kepler was with his analysis. Now, it turns out this ellipse has what's called a major axis that goes this way. That's the major axis. And of course, if you cut that in half, that length would be called the semi-major axis. And this one's called the minor axis. Okay. Now, if you realize what he's saying is the sun will be at one focal point. So the sun could be right there where that nail is, but there's nothing special at the other nail. And if you tried to consider what's the average distance between the planet and the sun, you might consider, well, there's a time period at which the planet would be here, in which case the distance between the sun and the planet would be about 1.5 semi-major axes. In other words, remember, this is this distance from here to here is a semi-major axis. In other words, it's half the major axis, right? Now, you could also consider that the planet will sometimes be here, in which case that distance is 0.5 minor axes, or somewhere along there, semi-major axes. So if you average those two, what would you get for the average distance between the sun and the planet?
One.
Exactly. So you took 1.5, you add 0.5 to it, you got 2, you divide that by 2, you get 1. So the average was the semi-major axis. Again, we're using that both as a thing, both as a line and as a distance. So, and the symbol we use for it is just plain A, and we actually normally measure that in astronomical units, so that A for the Earth is equal to exactly 1.00 astronomical units. Off the top of my head, 1 AU, you might definitely check this on your own, is on the order of 1.496 times 10 to the 11th meters. Okay, again, I put a little tilde there just to remind you that I'm remembering it off the top of my head, didn't look it up. So there's a good chance that it might be off a little bit. All right, so that's Kepler's first law. K1, that the planets orbit in elliptical orbits with the sun at one foci, and that's a really big deal. And it happens to be really awesome that he did it because the ellipses were so close to circles. Now, the other part 2, Kepler's second law, said that they sweep out equal areas in equal time. So if I can try to draw another elliptical orbit, if you will, I'm going to do something like that roughly. And let's draw our sun right here. What we mean by that is, let's say if I connect a line from the center of the sun to the planet, and it comes up right here, and then I connect another line from the center of the sun to the center of the planet, and it comes up here, okay? You can imagine that as making like a really big pizza slice for a weirdly shaped pizza. Okay. And let's say way out here, this far away from the sun, let's say that that took from day 0 to day 30. In other words, it took like 29, 30 days to go that distance. Well, if I tried to find a piece of pizza at the other end of the orbit that had the same amount of cheese, even though it's not nearly as long of a slice, you'd probably have to do something like go from here all the way to say here. Does that seem reasonable to you folks?
Yeah.
So what Kepler's saying is if that's the case, if these two areas are equal, then this also is day 0 and this is also day 30. And from that, you can reach the conclusion that clearly the planet speeds up when it's closer to the sun. Whoa, I don't know what happened. That's bad. So I'm going to say so you can think of it as the amount of cheese on the slice of pizza. If they're equal in the two cases, then the amount of time taken was equal. And what this says is planets speed up when close to the sun. Now, this isn't really what Kepler's second law is about, but I'll tell you, when I tell you Kepler's third law, it's not that easy to look at Kepler's third law and decide from that, hey, which is faster, which has the largest speed going around the sun, Mercury or Jupiter? That's kind of hard to tell from Kepler's third law. But this, even though it's not meant to do that, this actually is completely consistent with reality. And what I mean by that is the planet, when it's closer to the star, the sun in this case, goes faster than when it's farthest from the star. So you can apply that too, even though it wasn't meant for this, you can apply it too if you want to remember which one's faster, Mercury or Jupiter. Well, Mercury's closer to the sun, so it's going to go faster. Okay. So planets sweep out equal areas in equal time. That's Kepler's second law. And then Kepler's third law, we've taught, or I taught my students about this, at least in our lab, and probably you've done something similar to this in your lab. But basically what he did was he discovered that T, the period, and that's really how long it takes to make one revolution around the sun. And A, the semi-major axis, which is really that average distance, if you will, between the sun and the planet. If you make a plot of that and you try to get a straight line, which is what we've been doing in all of our graphing labs, then the plot turns out to be, or the graph turns out to be like this. And it doesn't turn out to be a straight line until you graph T squared and A cubed. When that happened, and of course, he only had 6 things to go from. He had Mercury, Venus, Earth, Mars, Jupiter, Saturn, and that was it. But when he did that, it became obvious that there was a straight line and that y equals mx plus b was true, only b was 0. And what that told you is that T squared is equal to some constant times A cubed. Well, let me offer you this. If we use the period in years, I'll subscript it right here, years. And if I use the the semi-major axis in astronomical units, and I'll put that here, we know that the period of the Earth is how many years?
One.
One. And hopefully y'all heard me earlier. We know that the semi-major axis for the Earth in astronomical units is
One.
one.
Big.
Yep, and that's exactly where the definition came from. So what does the constant have to be given this piece of data for our planets? Can you tell me what its value would be? Don't worry about its units.
1.
Yep. So it turns out it's going to be 1 year squared per astronomical unit cubed. Now, I'm going to tell you that we can take Newton's law of gravity and show that Kepler's third law is true. And by the way, all 3 of these laws will be proven in your calculus textbook. I'm almost 100% certain that every calculus textbook has that. So if you look in your calculus text, you're probably going to find where they did that proof. I'm just going to give you sort of a proof of Kepler's third law. And the way I'm going to do it is this. The summation of the forces, according to Newton's second law, is equal to an object's mass times its acceleration. If you consider a planet orbiting our sun, then you have the sun right here. And let's take, just for this case, a simple circular orbit. Oh, that was horrible. A simple circular orbit of radius r. Oh, that was bad too. Okay. And what I'm going to say now is this radius right here is big R. And we know that in order for something to maintain a circular orbit, the acceleration has to be a centripetal acceleration. And we know that Newton's law of gravity says that the force must be G times the mass of the planet, which I'll say is little m. So let me draw this over here. And I'll say this is big M. So times big M over R squared, that's the force of gravity. Well, that's got to equal M times V squared over R, where V is actually that velocity right there. But notice in terms of the period, V has to be 2 pi R over T. Does everybody see why that's the case? Everybody understand why V has to be 2 pi R over T?
Is because it's traveling around that.
Exactly. The distance it travels is sorry about that. Got some rude neighbors that won't stop ringing the doorbell. Yeah, the distance it has to travel is the circumference of the circle, and the time it has to travel is the period, what we call the period of the orbit, or capital T. So what I've done now is I have multiplied both sides of Newton's second law by R, so that you can see the R in the bottom of the right-hand side cancels out, and one of the R's in the bottom of the left-hand side cancels out. But you can also see that this mass right here, which is the mass of the planet, that cancels out as well. Now that we have that, I can rewrite this as G, the gravitational constant of the universe, over times capital N over R is actually equal to, and here's where I'm going to put in the value for V. That's going to be 4 pi squared r squared over t squared. So everybody see what I've done there? Now, with that in mind, I can go ahead and take and solve for t squared. So I'm going to multiply both sides by t squared. And the left-hand side will become just t squared. And then I'm going to divide both sides by gm over r. So what's going to happen is basically the same thing as multiplying by r over gm. So I'm going to get a r cubed right here, because the r on the bottom of the left multiplies by the r squared in the top. And what I'm going to have now is a 4 pi squared over the gravitational constant times the mass of the sun. Okay, so this is, in fact, Kepler's third law. And in fact, if you prove that 4 pi squared over gm is equal to 1 year squared per astronomical unit cubed, I'll give you extra credit. So this is an extra credit assignment. I'll write it up in the module and you'll see it. And I've got another one coming in a second. Okay, so that's an extra credit problem you can do. Basically, G is going to be 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. M is going to be the mass of the sun in kilograms. So you can get everything in terms of basically just seconds and meters. And if you use the number of seconds in a year, you can convert the seconds to years. And if you convert, if you can use the number of meters in an astronomical unit, then you can convert the meters to astronomical units, and that should give you a 1 there. Okay. Now, if you do this the big boy way, the big person way, where you actually take into account all the major deals. Like, for instance, there's no reason that the mass little m is much, much smaller than big M. In fact, it is with our planet. It turns out about 99.99, maybe even 0.999% of the mass of the solar system is entirely in the sun. So the little mass of the Earth is pretty small. But if you did it more generally, what you'd find in the denominator there is not just the mass of the sun, but you'd find the mass of the sun in parentheses with the mass of the planet being added to it. And in fact, the two planets' center of mass would orbit the center of mass of the system, so that there's a center of mass of the system that sort of sits still, and the Earth's center, say, would be always on one side of that center of mass, and the sun's center would be center of mass would be on the other side. That's what happens when objects are a little bit closer to their own size. Now, what we have now is we know Newton's law of gravity. Newton's law of gravity basically says that F in magnitude is equal to G, the universal gravitational constant of the universe, times M1 times M2 over the square of the distance between M1 and M2. Okay, remember, this gives you the magnitude. And then then Newton told us, by the way, the magnitude will be given by this formula, and they're always attractive. So what that means is the force will always act along a line connecting M1 and M2. If M1 and M2 are point particles, then it's just that one line that happens to go through those 2 points. But if M1 and M2 are not point particles, then it has to go from the center of mass of M1 to the center of mass of M2. And again, it'll be attractive, but along that line. That's how I gave you last time Newton's law of gravity in vector form. Now, we know that law exists, and what I'm going to ask you to do for another extra credit, for starters, your book does an example that's kind of neat, and it talks about the Lagrange points. So I definitely recommend you reading over that. But the Lagrange points, and there's several of them, are neat little places that Lagrange was able to find where you could put things in orbit and they would constantly sort of stay the same distance away from the Earth and complete their orbit in the same amount of time as the Earth did. So it's basically places where you can park satellites for doing constant observations of the Earth. One of which is, if you imagine the sun being, say, right here, and you imagine the Earth being, say, right here, this is obviously not to scale, okay? There happens to be a point right here, and I think that's called L1. There happens to be a point right there where you can put a small satellite, and it's got to be along the line connecting the center of the sun to the center of the Earth. You can put that satellite there, and it will in fact orbit the Earth, or excuse me, orbit the sun in the same amount of time that it takes the Earth to orbit the sun. So it's sort of like a protector satellite. It's always going to get information from the sun just a split second before us. And therefore, you know, if we had a solar flare coming at us, it could give us a little bit of warning, stuff like that. But the main thing is, give that example in your textbook and try and see if you can actually work that out to find out how far away from the Earth or how far away from the sun is that Lagrange point. That's not a bad problem. Now, the problem that I want you to consider for an extra credit is, let's say this is our sun. Okay, and I'm obviously not drawing this to scale. In fact, it's essentially impossible to draw a scale model of the solar system, because if you make the scale model of the solar system small enough to fit on a fairly normal size piece of paper, and I'm talking even poster boards and signs like you'd see on the side of the highway, in order for you to make the orbit of Neptune and Uranus fit, not even Pluto necessarily, you'd have to make the planets so small that you couldn't see them. And in fact, they would be, you know, probably on the order of the size of a micron or a microbe or something like that. But either way, what I'm going to do is I'm going to say, when the moon is in third quarter, whoa, I forgot it was left on that. So I'm going to say moon in third quarter. And what that means, by the way, is that, like always, except during eclipses, half of the moon is dark. It's not always the same half. That's the part that, like, Pink Floyd and people get wrong. But the main thing is, half of the moon is always dark except during lunar eclipses. In the case of third quarter moon, what's going on is the line that connects the center of the sun with the center of the moon is in fact at a 90-degree angle from the line that connects the center of the moon with the center of the Earth. Okay. So what that means is that the force on the moon due to the sun acts this way. That'd be F moon sun. And the force on the moon due to the Earth will act this way. And what I'd like you to do for extra credit is calculate the total force on the moon at that time. Okay, so you can look up, for instance, what the mass of the sun is. So you're going to have to find that. That's in the front cover of your book, which they have a section in your in My Lab and Mastering where you can look that up. So you'll need the mass of the sun, which is written like that. You'll need the mass of the earth, which is written like this. Whoa. Which is written like this. And you'll need the mass of the moon, which I'm just going to write like this. Okay. You'll also need this distance right here, which I can tell you is in fact about 60 times the radius of the Earth, but you can actually look it up. And you'll also need this distance right here, which I can tell you is very, very, very close to 1.00 astronomical units. Obviously, you want to use that in meters, though, or you won't get the force out in newtons. Okay. But the good news is this is an easy vector addition problem because clearly the force on the moon due to the Earth is at a 90-degree angle from the force on the moon due to the sun. So when it comes to adding those vectors, you can just square them, their magnitudes, add the square of the magnitudes, and then take the square root, and then just find the angle. Okay. Any questions on that? All right, so we've done quite a bit of stuff now. You can, of course, solve a lot of other problems with Newton's laws of gravity. I mentioned to you before that you can use the fact that gravitational force is G_m_m over r squared, and that will actually allow you to reach the conclusion that the gravitational acceleration, G, is in fact equal to the universal gravitational constant of the constant times the mass of the planet on which the gravity you wish to know is, and then divided by the radius of the planet squared. So that will always be gravitational acceleration. Oops. On the planet's surface. That's why I used the radius of the planet instead of some other distance r from the center. Okay. So we know that in fact, I gave you an extra credit where you can calculate that for the bottom of the Marianas Trench. You can calculate that for sea level, and you can calculate that for the top of Mount Everest. And you're supposed to even calculate the percent differences from them. And I think you'll find that it's a very, very small difference. Anybody have any questions on any of that stuff? Okay, well, let's try one sort of complicated problem. Let's imagine that we're going to have I'll make a coordinate system so we can have something concrete to work with. This is going to be my y-axis. This is going to be my x-axis. Okay, what I'm going to do is I'm going to put one object at the origin, and I'm going to say its mass is equal to, let's say its mass is equal to 1.5 times 10 to the 6th kilograms. Okay, and let's put another object over here. And this distance is going to be, let's say, 500.0 meters. And this object's mass, which I'll call M2, is going to be 1.5 times 10 to the, let's say 6 meters as well, or excuse me, kilograms as well. Okay. And then right up here, I'm going to put a mass M3 is equal to, let's say 1.5, no, let's say 1.00 times 10 to the 5th kilograms. And let's say the distance here is 500.0 meters. And the distance here is 250.0 meters. And I would like to calculate F3 total. Okay.
That's 4, so the mass of 3.
Yeah, it's the total force on mass 3. So mass 3 is going to feel a force from mass 1, which I'll go ahead and label mass 1 down here. And it's going to feel a force from mass 2. And both of those will add vectorially. And from that, I'm going to have to figure out what the total force is. So what I know, according to Newton's laws of gravity and motion, is that the force is attractive in all these cases. And therefore, I know that the force on 3 which I write as F3 due to 2 is this guy. And I know that the force on 3 due to 1 is this guy. Now I can work out the details. For instance, I know this distance right here is 500 meters. So basically I can say 500, 250. And of course, this is a right triangle here. And what I need to know is this angle right here, which by the way, happens to be the same as this angle right here as well. So hopefully everybody sees that. Let me make that a little better looking. Can you see that this triangle, this 500, 250 triangle is the same as the left one? And in fact, if you make a mirror image of it, you'll get the right one. So the two thetas are the same. So what I can, yeah, that makes sense, right? So what I can do is I can say theta is going to be equal to the inverse tangent of 250.0 meters over 500.0 meters. And that should give me basically inverse tangent of 0.5. So I'm going to do tangent inverse 0.5, and I get 26.57. I'll say 26.565 degrees. Okay, that had 5 sig figs on it. This has exactly 5 sig figs. In fact, the next number was 1. So I'm not really cutting off anything by doing it, but I will add this extra digit 1 there. So I have 1 extra sig fig. Okay. Now, what I need is the magnitude of F31. Well, that's just 6.67 times 10 to the negative 11th newtons meter squared per kilogram squared times the mass of 3, which is 1.00 times 10 to the 5th kilograms, times 1.5 times 10 to the 6th kilograms, all of that divided by the distance between them. Now, in this case, where you can also solve for the hypotenuse, which we're going to need, this hypotenuse is 250 squared plus 500 squared. So if I do that real quick, I'll say 250 squared plus 500 squared. Take the square root of that, and I get 559.02. And actually, I'll call that 0.017 meters, and that gives me 1 extra sig fig. So I know that distance is 559.017 meters squared. Sorry for writing that in a different color. 6.67, basically what I was shooting for by using 1.5 is 6.67 is about 10 times 2/3. And of course, 1.5 is 3/2. So that's why I was trying to use those numbers where it work out kind of nice, but I just threw that away in the middle and started to not worry about it. So I'm going to do 6.67 e to the negative 11 times 1 e to the 5 times 1.5 e to the 6. That gives me about 10, which is what I expected, given that it's 2/3 versus 3/2. Now I'm going to divide that by 559.017 squared. That gives me a magnitude equal to, crap. That gives me a magnitude of about 3.202. Notice I'm only using 2 sig figs for the masses. So really, I got no business having these 2 here. So 3.202 times 10 to the negative 5th newtons. That's a pretty small force. Now for the other one, notice they're the exact same. So F32 is, in fact, since they're the same masses, 1.5 times 10 to the 6th, they're the same mass, 1.00 times 10 to the 5th, and the same distance away, we get 3.202 times 10 to the negative 5th newtons for both of those. I think you can see what happens. Obviously, we've got a y component and another y component that add to make double the y component. But we also have an x component that cancels out with an x component like that. So in fact, all I really need is 2 times the y component, and that'll be the total force. So F3 total is equal to 3.202 times 10 to the negative 5th newtons times cosine of 26.5651 degrees. I'll put a negative in front of that, and I'll put a j hat after it since it is a vector. So I want to multiply this times parentheses cosine of 26.5651, and this gives me 2.86. Remember, we only had 2 sig figs from the force, so 2.86 times 10 to the negative 5th newtons in the j hat direction with a negative. So that's it. That's the way you can use a formula that gives you a magnitude and then make sense of it vectorially. You calculate the magnitude, then you find or create some line that is parallel to it. Then you construct a right triangle or some kind of triangle, so you can use trig to figure out certain angles. And then you can just eliminate components or add components or whatever. So does anybody have any questions on that?
You said the x component cancels out?
Yes, because the x component points to the right for F32 and it points to the left for F31, and they both have the same magnitude.
I see. Okay.
They also have the same theta, so sine of theta is going to be the same for each of them. Anybody else have any questions? All right, well, we finished just in the nick of time. Next time we'll jump into, I think it's chapter 7, where we start where we start energy methods. So I'll jump in with calculating work. We'll use a dot product there. That's a new mathematics that hopefully you already know just from trigonometry. We're going to also use the fact that the calculation of the actual work is what we call a line integral. So we're actually going to be learning some Calc 3 stuff, but this semester it's not going to matter very much, but next semester it'll be a little bit more problematic. So just be prepared, but we are going to be doing dot products and then integrating those, and that works. So yes, I did move the midterm. The midterm is now going to be the Wednesday after we get back from spring break. Spring break is March 5th through March 12th. That means on March 15th, ideally what I'll have is have you guys start maybe as early as 20 minutes early or finish as late as 20 minutes late, and then I can give you a larger amount of time to complete it. If I have any one student email me and let me know they can't show up either early or stay late, then I'll have to cancel that, and everybody will just have to take it from our normal class meeting time, which is 5:20 until 6:40. But also keep an eye out. I will be making probably test 3 and one of them's already up, but test 3 and test 4 are going to be up, and they'll be excellent practice for the midterm, by the way. And I think what I'll do is I think test 3 is already due on the 26th, which is just coming Sunday. I'll probably make the test 4 due like on the 12th or something like that. If it not, it'll be the 5th, but I'm leaning towards the 12th. So just keep an eye on that, the practice test and the regular test. Of course, whenever I do put up a new test, I always send out an announcement, which comes out as an email too, so y'all can find it that way. I will wait for the last person to leave just in case anybody has any questions, and you guys are free to go. Thank you for coming. Does anyone need me to keep the screen up here, or can I go ahead and start erasing, or at least showing something other than the screen? I actually started really weirdly and skipped a bunch of pages. So I'm going to erase that. Oh, not that way.
So you were saying, sorry, I missed it. What were you saying was very good practice for the midterm? The practice test?
Yeah, the practice test for test 3 and test 4 is actually going to be very good practice, period. Not only for the practice test, but it's also going to be good practice tests for the midterm, because the midterm is comprehensive. I will also put up a practice midterm, and that'll be more geared towards specifically the midterm. So hopefully that'll help too.
Awesome. When will that be going up, the practice midterm?
I suspect it'll be up before the weekend, but if not, it'll definitely be up by Monday.
Sounds great. Thank you.
No
The
problem.
midterm is through chapter 8, right?
So far, that's what I'm thinking. I might go a little bit further, but as far as I can tell right now, I'm leaning towards chapter 8. It might even be, depending on how things go, I might even just stop it at 6. I haven't completely decided.
All right, thank you.
No problem. Anyone else?
I did actually have a quick question.
Yes.
Will the practice tests and stay up like past when they're due so that we can still practice them? Is that an option?
No, the reason why is because I give you a good deal of extra credit for doing it before the test, but the practice chapters will be up. So you can always have practice. It'll just be on those chapter practice.
Is there a way that we could still get like a list of the questions? Maybe not like be able to take the practice tests. That way people who took it after the test would get that credit. Do you know what I'm talking about? Like, I don't know.
Right.
I feel like if tests 3 and 4 are good practice for the midterm, I feel like they should be available after those things are due.
Gotcha. I understand that. And they are, but they are only through the practice chapters. So I never, ever print them out anyways, or any answers. But if you go on, let me stop this share for a second. Stop share. If you go to, for instance, let's do this share. I am going to go here. The questions that I use for your practice tests are in fact identical to the questions that I use in these. Practice 1, practice 2, practice 3, only they're just per chapter. So those are always available. You'll notice I have them available till May 9th. So
Okay.
yes, you actually have access to those till the end of the
Just in a different
semester.
format. Okay.
Yeah.
All
And
right.
it's
Thank
just
you.
per chapter. I think that might be a little more helpful even than what you're looking for.
Okay. Thank you so much.
No problem. See you.
Wait, so I'm sorry, I'm like kind of looking at your being nosy, looking at your thing. Are you going to require us to use Respond Us for the practice midterm?
Just once to make sure your Respondus lockdown browser and Respondus monitor works. In fact, I might not even put questions in it, or if I put questions, it'll be like 1 and it's not going to be graded. It's just a matter of one of those things. What you'll find out is even if you use Respondus lockdown browser or Respondus monitor once, you might find that it needs to be updated before it works. So if you go to take your midterm on the day that it's due, all of a sudden it'll stop you and say, wait, you've got to update this. So by me doing that and you actually completing the practice Respondus, you will have your software up to date, and then you'll have just a regular practice midterm that you can take 1,000 times if you want.
Okay, thank you. I just wanted to make sure.
Yeah, it's kind of weird that I do that, but it's mainly just for that, so the software will be up to date. Anyone else? Carter, Didio, everybody's leaving. Well, thanks everybody for coming. Carter's still here, but I'm not sure they're actually still here. So I'm going to go ahead and assume they're not. And hope you all have a wonderful weekend. Thank you for coming. Bye-bye.